So here's a puzzle. We know that silver chloride dissolves to form silver ions and chloride ions, and its solubility is very, very small. It's something we think of as forming a precipitate. So if we look at the solubility of silver chloride in sodium chloride, you can see that its predicted solubility is just silver chloride is 1.3 times 10 to the negative fifth moles of silver chloride per liter. That's really small. And we would expect, because we can calculate using the KSP, that as we increase the concentration of chloride ion from sodium chloride, we would decrease the solubility. And it turns out that at first, that's what happens. But then experimentally, it goes in the other direction. Solubility starts going up and up and up. So something else must be happening. And what's happening is the formation of a complex ion. So when free silver ions react with chloride to form this complex ion, they have what we call a KF. F for formation, and KF is for the formation of a complex ion. So let's review complex ions just a little bit. We have a metal ion. That's going to be our cation, and it has small neutral or negative species that we call ligands. And these have to have lone pairs because these lone pairs are what are attracted to the metal ion in what we call a coordinate covalent bond. In the coordinate covalent bond, it's just like any other covalent bond, but the electrons come from just the chloride. None of them come from the silver ion. So you can see with complex ions, we can take the free metal ion and the ligands and form a product, the complex ion. And we can write a balanced net ionic equation and a KF for lots of different complex ions. So here I did the first one. We have aluminum and 4 hydroxide ions making tetrahydroxoaluminate. And the KF is just products over reactants, just like they've been. So pause the video and try writing the net ionic equation and the KF expression for both the cobalt and the iron complex ions. All right, let's see what you came up with. Both of these have the ligand to the 6th power because there are 6 ligands. It is hexacoordinate. It has a coordination number of 6. We were able to figure out the charge of the cobalt ion because ammonia has no charge, and the whole thing's +2, so it has to be a cobalt +2. And we figured out the charge on the iron ion because cyanide is a -1, the whole thing is a -4, so only a +2 and -6 would equal -4. So this is how we write the KF for the formation of complex ions from a free metal ion and ligands. But what we were talking about is dissolving precipitates. And in order to do that, we're going to need to take a look at the net ionic equation for the formation of the complex ion and for the KSP, dissolving the precipitate. And in order to do that, we're going to have to combine some reactions. So this page isn't in your notes. We'll just talk about this. Here I have carbon monoxide and water making carbon dioxide and hydrogen gas. If I add 2 substances in the reactant side, they turn out to be multiplied in the denominator. If I add 2 substances in the product side, they're multiplied in the numerator of the K expression. If I added another chemical over here, it would end up multiplied over here. If I added another chemical in the reactants, it would end up being multiplied in the denominator of the K expression. So if instead of just adding one more substance, I add two more substances in the form of a balanced equation, I'm now adding reactants and adding products. And what I do is I multiply their equilibrium constants. So if I add these equations together and cross off what's the same on both sides, we get rid of the CO, we get rid of the CO2, and we can see that iron and water make iron 2 oxide and hydrogen gas. K expression for one and the other, multiply them to get the third. Why would we do that? Probably because it's experimentally possible to get the first one, experimentally possible to get the second one, and experimentally difficult to get the third one. So this allows us to use lots of different equations that we can measure their equilibrium constants and predict the equilibrium constant for something where we can't measure it as easily. So let's take a look at this in the context of dissolving precipitates. Here I have nickel 2 sulfate, a soluble green solution, which nickel provides the green color. And if I add some hydroxide, you can see the precipitate starting to form. So what we want to be able to do is to dissolve that precipitate. And so we're going to add ammonia to dissolve the precipitate. So I have a base in there already, and I'm going to add another base to try to dissolve it. Let's see how it works. So if I start adding ammonia, you can see the blue start to form, and that blue is the complex ion with nickel with 6 ammonia molecules attached to it. And it takes a little bit to dissolve. It actually takes quite a lot for it to dissolve. So you can see we're adding the ammonia, and eventually we're going to get tired of using the pipette and just add straight from the bottle, and you can see that it's starting to clear up as the blue complex ion has formed. So let's take a look at that in a quantitative way. So here I have my equation of the nickel ion and the hydroxide ion making the precipitate. And here is the equation of taking the precipitate and adding ammonia to make the complex ion. And so this is the equation we want to focus on. And what we're going to be doing is we're going to combine the equations, the KSP and the KF. So to do that, first I need my equations. I have nickel hydroxide dissolving into nickel ions and hydroxide ions. That's the KSP. And I have nickel ions and ammonia forming the complex ion. That's the KF. If I cross off the things that are the same on both sides, so I cross off nickel ion, I end up with my nickel hydroxide dissolving in the presence of ammonia. Now to find their equilibrium constants, I'm going to use my reference tables. It's the KSP for nickel 2 hydroxide and the KF for hexaamine nickel 2. Take those two numbers and multiply them together, and I still get a number that's pretty small. It's still times 10 to the negative something, which means I'm not going to see very much of this. But we saw in the video that it did dissolve. So that actually leads into something we're going to talk about in the next section, Le Chatelier's principle. But what we were able to do is take the nickel hydroxide and make it more soluble than it would have been just by itself. So let's take a look at how that works for another equation. You have your KSP charts, So pause the video and calculate the molar solubility of silver iodide. That's just a regular KSP problem, an equilibrium problem. When you're done, we'll take a look at that, and then we'll find the equilibrium constant for this reaction. All right, this one was actually pretty easy as KSP problems go. It's the silver ion concentration times the iodide ion concentration, so it's x squared. Molar solubility, about 9 times 10 to the minus 9th. Silver iodide is pretty insoluble. So let's see if I can combine the Kf of silver cyanide and the KSP of silver iodide to try to make it more soluble. So pause the video, try writing the net ionic equations for the KSP and the Kf, find their Ks, write them in this box, multiply so that you end up with the equation at the end. That is our target equation. So pause the video and see if you can do that. All right, so I took my silver iodide and tried to dissolve it with a very small KSP. It does not want to dissolve. And I took my silver and my cyanide, and it has a very large Kf. So when I multiply those two together, this is a pretty big K. Not a huge K like this one, but big enough that the silver iodide is going to dissolve in the presence of cyanide ions. So that's how we can take ionic solids that don't dissolve, and by adding them with a second reaction, make them dissolve. So what we're doing is we're taking something that is not likely to happen with a very small K, mostly reactants, combine it with something with a larger K, mostly products, to force the first reaction to somewhat happen. That happens a lot in our biological systems. We're going to talk about that on another day. So you can see from the previous slide that we have KSP in pure water. The molar solubility is really small. And if we add cyanide, it becomes much more soluble. And we can actually calculate the molar solubility of silver iodide in a 0.1 molar sodium cyanide solution. Our net ionic equation, the cyanide's a spectator ion, so we just have the silver iodide and cyanide ions making the complex ion. So pause the video and set up the rice problem. So hopefully yours looks like mine does. I have 0.1 molar cyanide, and there's two of them, so it's minus 2x, and the complex ion and the iodide ions start off as 0, so those end up as x. Now, I'm not going to make you go through all the algebra, because we end up with 80,000 is x squared over 0.1 minus 2x parentheses squared. And you certainly don't need to write down solving the quadratic, but we end up with x is 0.05. Remember, x is the molar solubility. So the key take-home that we're looking at right here is the idea that in water, the solubility of silver iodide is 9 times 10 to the negative 9th molar, and in cyanide solution, it's 0.05, which is times 10 to the negative 2nd. So that's 10 million times more soluble in cyanide solution than it is in water. That's a pretty significant difference. And that's how we can use Kf, or complex ions, to dissolve precipitates. That's what you did in the qualitative analysis lab. You did that several times to get precipitates to dissolve. You did it with the copper precipitate to form the copper ammonia complex ion. You did it with silver chloride to get the silver ammonium complex ion. And all of these are ways of forcing a reaction to happen that wouldn't happen on its own. So we're going to skip this page for just a minute. We're going to come back to it, and we're going to focus on adding reactions again. The first one, we have EDTA, which is a hexadentate ligand. And it wraps itself around metal ions, and so we can use EDTA to remove poisonous lead carbonate from a system, taking the precipitate and dissolving it into something that can then be washed out of our system. We can also, and we did this in the lab, take zinc hydroxide, that makes a precipitate, and add excess hydroxide to dissolve it. So I'm going to let you try to find the KSP for lead carbonate and zinc hydroxide, and the KF for lead EDTA complex ion, and another zinc hydroxide complex ion. So find the KSPs and KFs, write the net ionic equations, and find their Ks. So pause the video, take a couple minutes, and try those. When you have the first one done, we'll check that, and then we'll pause and do the second one. So this is what it looks like for the first one. It doesn't matter which one you put on top or the bottom. I just happened to do this one on top. I have my lead ions, which end up getting canceled out. They react with EDTA to form a complex ion with a really big K. And lead carbonate dissolves to form lead ions and carbonate ions barely at all. We would think of that as something that is insoluble, something that doesn't dissolve. So if I add these two equations, I multiply their equilibrium constants, and I get something where lead carbonate in the presence of EDTA will dissolve. That's super useful if somebody has lead poisoning, because that EDTA will wrap itself around and wash the lead out of the system. So now pause the video again and try the zinc hydroxide. And you can see the excess zinc hydroxide ions will cross off some. So we cross off two of the hydroxides here and two of the hydroxides there, making it a 2. Oops, way too big. Shrink that. Makes it a 2 hydroxides, and the zinc ions also disappear. So we end up with zinc hydroxide and 2 more hydroxide ions, making tetrahydroxozincate. Multiply their equilibrium constants, and we end up with something that has a pretty good mix of reactant and product. And we're going to talk in our next lesson about how we can force it to make more of the complex ion. So now you know how to add reactions to find new equilibrium constants by multiplying their Ks, and you know that we can take an insoluble solid and dissolve it by forming a complex ion. If you have any questions, as always, make sure you let me know. You should now be able to finish the KSP and KF homework. Good luck.